Excellent. Yeah. Big plans for this weekend, hopefully. Uh, okay. Good. Well, let's get to it. So, wanted to start talking about um, kind of a new thing, or mostly new. Most of the series we've looked at thus far. Oh, sorry. Let me get the thing over to the. Most of the things that we've looked at so far, series that we've looked at so far, are only had positive terms. Okay, with one exception. The geometric series. So what happens if we have a series that has both positive and negative terms? First thing I'm going to define is an alternating series is something that looks like that. Okay, so it has two pieces. It has uh, an a sub n term that's non-negative, okay, like before, but we have this thing in front that's basically -1 to some power, and depending on whether or not that power is odd or even, will determine whether or not the thing is plus or minus. Okay, so this series will alternate, and the terms, one term will be plus, the next one will be minus, and then so on. Okay. All right. So we've seen an example of this. Or so let's take, for example, the situation where I had um, -1/2 to the n. What kind of series is that? Pray tell. Yeah, it's geometric. Okay, so what are the terms of this thing? Well, what's the first term? Okay, why? Because I started at n equals 0, not n equals 1, right? Okay, so then it'd be that minus this plus that minus this, and so on. Okay, what does this add up to? Well, first off, does it even converge? All right, so what's R here? Thank you. So it sums to the first term, which is 1, over 1 minus the common ratio, and that's 2/3. Okay, does that make sense? Yeah. So geometric series, well, and I guess maybe to an extent the telescoping ones, are the only series that we've looked at thus far that had both positive and negative terms. Okay, so right. So now what we want to do is, well, what happens if we have just any old series? Okay, so let's look at another example. Let's look at this series, -1 to the n plus 1 times 1 over n. Okay, first off, what does your gut tell you about the convergence or divergence of that series? What's the part that your mind is fixating on, perhaps? Well, what about if I didn't have that -1 to the whatever? Then what kind of series would I have? Harmonic. And what do we know about the harmonic series? Huh? It diverges. Okay. This is a lot like the harmonic series, right? It's got the 1 over n part, but it's alternating. Does that change how it behaves? Well, possibly. right? It's not, you guys agree that this is not exactly the harmonic series, it's just suspiciously similar. Yes? Okay, so does this thing converge or diverge? Well, why don't we do a little bit of just Mathematica futzing around. That's a technical term. So let me switch the input to Mathematica. Yeah. Okay. And let me blow up it so that you guys can see better. All right, so what I want to do is I want to start to look at partial sums of this series. Okay, so what I'm going to do is I'm going to define a function, and I'm going to define it to be the sum of -1 to the I, or let me do k because it's easier to see, k plus 1 times 1 over k, where k will range from 1 to n, where n is a variable, okay? So if, for example, I type in what is f of 1, then that's 1, the first term, okay? What would f of 2 be? Okay, that's the second term, but how have I defined this? I've defined it as the partial sum. So if the second term of the series is minus a half, and the first term is 1, then the second partial sum would be 1/2, right? 1 minus a half. Okay, so with this function f sub n that I've defined, I really should have called it s sub n for the nth partial sum. Okay, so the reason I wanted to do that is let's just see what happens if I do f of 1, or sorry, f of whatever for large values. Okay, so f of 2, a half, f of 3, 5/6, 47/60. Okay, I don't know what the heck that number is, but well, let me actually just do this. Oh, I have to do, I don't know, it's, so I can't do a straight plot because this thing's only defined at whole numbers, and um, I forget what the command is called. List plot. Well, whatever. Okay, it's not important. But the point I wanted to go for here, though, is that what happens if I look at f of 100? Well, that's some horrible fraction. I don't know what that is. But let me look at a numeric approximation of it to 10 decimal places. Okay, that. All right, fine. It's going to take a minute. All right, does this thing look like it's converging? Yes. Okay, what was it supposed to converge to? Well, okay, so let me make sure I'm not messing something up here. It is, yeah, it is. I mean, it's 10 million, right, things, right? And then it's got so it's calculating exactly the 10 millionth partial sum and then evaluating it to 10 decimal points, right? So the order here matters. So, all right, it's going to run. Well, we already know what, sorry. So what does it look like this is approaching, or does it? 0.7, maybe it's 0.69, blah, 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 right? Okay, not entirely sure. All right, we get the idea. Let me stop the evaluation here. Okay, so let me crank this back down to something more reasonable. Well, maybe that wasn't reasonable. Okay, now I think I've managed to crash it. There it goes. Okay, so we get that, right? So it turns out that this thing converges to the log of 2. Okay. Now, why does it converge to the log of 2? How do I know that? We'll be able to see why starting sometime next week or maybe early the week after. Yes, exactly, because I'm a doctor, trust me. All right, but it converges. Now, does that surprise you? Why does it surprise you? Because the harmonic series diverges, but simply making this thing alternate plus minus is somehow enough to make it converge. Probably, right? And that's basically the idea, right? So we have a theorem. So this converges, or seems to converge by Mathematica experiment. Okay. Now I haven't proved that it converges, but I've maybe um, gently hinted that it probably converges. Okay. All right. So there's a theorem, and it's the alternating series test. Oops. Okay. So theorem. If you have a series, an alternating series, that means it's of the form -1 to the n times a sub n, and the a sub n term is never negative. Okay, so it's a positive or possibly zero sequence. Okay, if the following two things are true, first is that it's decreasing eventually. Okay, so what I mean by that is if the series bounces around and is increasing and decreasing and increasing and decreasing for like 10,000 terms, but after that 10,000th term, the terms are all going down, that's eventually decreasing. Okay, so what do we care about in terms of series convergence or divergence? Do the first 10,000 terms really matter? Not really. Okay. Now, if I delete the first 10,000 terms, I might change the number to which the series converges, but I'm not going to change whether it converges or not. Okay. Why is that true? Well, 10,000 terms, that's a finite number, right? If I mess around with a finite number of terms, no problem. It's the tail of the series that matters, meaning what happens when you go off to infinity. Okay, so that's what I mean by eventually decreasing.
Like if you had a series of one half, 1/4, whatever.
Mm-hmm.
If you took off the first one, wouldn't the number go to a smaller number?
It would change the number it converges to, yes, but it wouldn't change that it converges. Okay, so yeah, now that's a distinction, right? That a lot of times um, with these series, I can tell you, or you guys can tell me whether or not a series converges or diverges. but you can't necessarily tell me exactly what it converges to. Now, you could estimate it numerically by doing kind of this Mathematica business, and that's cool, but you can't tell me precisely what it converges to, okay? So if you lop off some terms, yes, you will change what it converges to, but it'll still converge if it converged before, okay? All right, so that's what I mean by eventually decreasing, that it might take 5 or 10 or 1,000 or however many terms before the sequence A sub n starts to uniformly decrease, and that's okay. It just has to eventually be always decreasing. Okay, the second requirement is that the limit of the A sub n sequence is 0. Okay, if both of these things are satisfied, then the series in question converges. Okay, if either one is not satisfied, well, then you don't know. Well, okay, actually, no. If number 2 isn't satisfied, then the series definitely diverges because that's the nth term test, right? Okay, so let's apply this to the series we were looking at a moment ago. So let me scroll up slightly so that we can see everything at once here. Okay. The sequence, so what's A sub n in our example that's at the top of the screen? One over n. Is the limit of that thing 0 as n goes to infinity? Yes. Okay. Is it decreasing? Also, yes. So we're good. So by the theorem, that series must converge. Good, it converges. Now, the fact it converges to the natural log of 2, we have not demonstrated it, but we'll talk about that next week, or maybe early the week after. I don't remember. Okay, is that all right? Yeah. Well, and the fact that it's alternating, right? Because if I didn't have that -1 to the n part, I wouldn't have an alternating series, right? So I can't talk about the alternating series test if my series isn't alternating. Yes? Not necessarily, but often, yeah. It's got to be something that's decreasing, which 1 over somethings tend to do, right? Makes sense. Okay, good. So that's the alternating series test. Excellent. All right, so let me hold on. Let me just double check what I wanted to talk about next in my notes here. Ba, ba, ba. Okay. Let's talk about. Sorry, I need more screen here. All right, so let me go back over to Mathematica to demonstrate this, and then we'll write it up formally. So make sure the stream switched correctly. All right, so we're here in Mathematica. Great. All right, so what I want to do is I want to compute. Here we've computed 1,000 terms of that sequence. Okay, and I told you guys that the exact value for the series is the log of 2. Let's just take that on faith for the moment. Okay. Now, certainly, if I only add up a finite number of terms, I'm not going to get the log of 2, right? Because I've left off a lot of stuff. But I should be relatively close to the correct answer. And the estimation theorem, what we want to do is think about, well, how close are we? Okay, so look here. We previously computed 1,000 terms added up, and the numeric estimation of that as a decimal was the 0.692 blah, blah, blah. Okay, and logarithm of 2 as a decimal to 10 decimal places is 0.693, blah, blah, blah. Those are pretty close, right? How close are they? Yeah, really close. Well, let's just, well, yeah, well, let's just compute it, right? What are we really talking about here? I'm talking about, well, here, let me copy this up to here, and let me do, let's do n of f of 1,000. Well, let me do this. Okay, so what I've done here is I've taken the absolute value of the difference. Well, what did we call the absolute value of the difference when we were doing this with integrals and stuff? It was the error, right? So if I chop off terms after the 1,000th term, then I've committed numerical error. How big is that error is my question. Well, in this case, what is the difference? And I took the absolute value just because I don't care if it's too big or too small. Yeah, we're in the 10,000th place. Could I have guaranteed that? Well, maybe. Okay. So what would be, here I added up how many terms? I added up 1,000. What is the 1,001st term? So this would be the first term that I excluded. What is the 1,000th term, or sorry, 1,001st term of that sequence? 1 divided by 1,001, right? Right, sequence, right? The first term of the sequence A sub n, right? So, because what would this series be, right? It's 1 minus a half plus a third minus a fourth plus a fifth, my blah, 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 dot, 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 minus 1 over 1,000. And then the next term would be plus 1 over 1,001. But I left that and the rest of them off, okay? So what is 1 over 1,001 as a decimal? Well, let's just compute it to 10 places. Okay, so what I want you to do is concentrate on this number and that number, okay? Which I've highlighted their sources on the top there. What can you tell me? The relationship between those two numbers, the bottom two. Okay, so remember, what's labeled there as out 11 is the actual error, and what's labeled there as out 12 is the value of the first term of the sequence that I omitted. No, this is math class. We don't care about sig figs. Yeah, okay, it happens that there's 3 zeros before you start to see anything. Okay, actually, yeah, roughly speaking, that seems reasonable. Okay, but you're making this too complicated. Well, one of those is clearly smaller than the other, right? Yes? Yeah, okay. Well, does this matter that I went out to the 1,000th term? What about if I went out to the 2,000th for my next trick? So if I go out 2,000 terms, then what would be the first term that I omit? The 2,001st term. Okay? All right, I'm going to omit those two numbers because I don't care about them right now. All right, so what's the first number? The actual error. What's the second number? The the first term I omitted. What do you notice about the error? Well, okay, it does seem to be about half as big. That's, I think, coincidence. Yeah, we have less error than we did before, and that makes sense because we went further out in the series, okay? But the error is smaller than the first term we omitted, right? Well, okay, so I added up all the terms up through 1 over 2,000, right? So the first term I didn't add was the 1 over 2001, okay? 1 over 2001 as a decimal is that bottom number, the 0.00499, blah, 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 right? So the error I committed by adding up only 2,000 terms was this 0.0002499, blah, 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 right? The value of the first term I omitted was the 0.0049, blah, 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 right? Do you guys, I mean, it's pretty clear. The actual error is smaller than the first omitted term. I mean, you get, there's the actual error, there's the first omitted term. You guys agree that 0.00024 is less than 0.00049? Definitely, okay? Is this always true? Yes, that's the theorem, okay? So what I've done here is to try to demonstrate numerically why this theorem makes sense, and then we'll state it formally in a moment, okay? Is that all right? Okay, so if you add up a series, an alternating series, and you chop it at a certain point, the difference between the true answer and your estimation is no worse than the first term you omitted. Now, quite likely it's a little better than that, okay? But now this should ring bells, ding ding, right? What does this feel like? Well, how did we do numerical integration? We had numerical integration schemes like left-hand rule, right-hand rule, trapezoid rule, and so on, right? And we talked about the error estimation formulas for them, right? So that the error committed is no worse than this thing. Yeah, okay? So there was an inequality, right? That the error, the true error, is no worse than this estimate. And for the error estimation formulas for numerical integration, those estimation formulas were actually kind of complicated, right? Because they had b minus a to the something, they had a k whatever, and then they had a something into the something in the denominator, right? They're kind of complicated formulas. This estimation theorem is actually a lot simpler. It just says if you add up the first 100,000 terms, your error is no worse than the 100,000 first. You add up the first 10 trillion terms, your error is no worse than the 10 trillionth and first. That's it. Yeah. Okay. So let's write out formally this result, and then we'll go back to Mathematica to do some other chateladding. All right, Elgato. All right. So the error estimation formula saith thus. Okay, so notation, we've got an alternating series, and first off, this doesn't make sense if the thing is a divergent one, so I have to have a convergent one to begin with. And let's say that the number to which it converges is L. Okay, what is L? Often I don't actually know. Okay, in the example that we were working with Mathematica, the alternating harmonic, I happen to know that it converges to the log of 2, but that's because I cherry picked a special one, okay? So often I don't know what L is, I just know that it exists. All right, and then, hang on one second. S sub n is the nth partial sum, okay? So what was S 1,000 would be the first term, the second term, the third term, the fourth term, all the way up to 1,000th term added together, okay? Yes, Donovan.
Does it have to be alternating to use this?
Yes. Okay. Uh, yes, it does. Well, okay, for the 1 over n series, it would diverge, right? But if I did this, like, say, for example, for the 1 over n squared thing, now we could kind of cook up similar results for non-alternating series, but this result specifically is uh, only applies for alternating series. Okay, then okay, Sn minus L, absolute value. What is this quantity? What do we call that? It's the error, right? Because S sub n is your partial sum, so that's your estimate of the sum. It's not perfect, right? Because you stopped adding things at some point. And L is the true value of the sum. The difference between those with absolute value, because I don't care about. Yeah, well, it could be a negative number, right? Because I could be like, uh, no, not necessarily. It depends on which term you.
Like, how can you add up stuff and make it more?
Oh, because half the terms are negative.
Oh, this is just for alternating.
Yeah, exactly. Right. So when I say add, half the time I really mean subtract because my sequence is flipping plus minus plus minus plus minus, right? So half the time adding is really subtracting. Okay. Yeah. No. Fair point. That's. We're still talking alternating series. Okay. Good. Yes or no? Gucci. Okay. So that's why we've got the absolute value there because um, depending on whether or not we've stopped on a plus or we stopped on a minus, we could either be too hot or too cold, so to speak, in terms of the Goldilocks analogies, right? Um, do you guys know Goldilocks and the Three Bears? Yeah, it's a children's story, right? I'll tell you later. Okay. Okay. So anyway, point being, depending on whether or not we stopped on a plus term or a minus term, our estimation may be slightly too high or slightly too low. Do I care whether or not I'm slightly too high versus low? Not really. What I care about is how close am I to the true answer, and that's why we've got the absolute value there to define error. Okay. So what this theorem says is that the error is less than the first term you left off. Okay, so if I go up through 10,000 terms, the first term I left off would be A sub 10,001. Okay, and as we saw with our numeric experiment, sometimes it's quite a bit less than that, right? But it's guaranteed that it will be less than it. How much less? That depends, but it will be less than. Okay, does that make sense? Okay, so if we think about this in terms of like what we did with the numerical integration stuff, there were really kind of a couple ways that we talked about that. One was saying, okay, if you do the trapezoid rule with n equals 8, how good is your estimation? And you calculated that, right? The other was something like, let's say that you need the correct, or you need your estimation to be within 1 in a million of the true answer. How many terms do you have to use to make that happen? Yeah, you have to solve the inequality. Well, we can do the same sort of thing here. So, how many terms do I need to add up so that this thing is correct to within a millionth of a unit? Well, let's figure that out. All right, so practice. Well, okay, I'm a little biased here because I have written in my life lots of Greek letters for two reasons. One, I'm a mathematician, and two, I study Greek, right? So not only do I write out Greek letters, but I also write out sequences of Greek letters to make Greek words, right? And so it's as natural to me as writing English. Um, but I've been doing it a long time, longer than most of you have been alive. So get off my lawn. Well then, a B minus sigma, huh? Yeah, yeah. You're about to have an F star. All right. Okay. And then we could like get some like shading action going and yeah, sort of. Right. And then I could put like there's a little sparkle. It's like a little reflection off of it. And then I could use like give it like angry eyebrows and like spines and and then I could put like a beefy arm off the side for good measure, right? Now, how many of you guys have never seen or heard of Trogdor the Burninator? No? Homestar Runner? Never mind. Oh, we're going to sidetrack for a second. Trogdor the Burninator. Homestar Runner. It was so back in the day before YouTube, people made flash animations, and there was this one guy who made a comic type thing called Homestar Runner, and Trogdor the Burninator was one of his characters. So, um, yeah, go watch that video. It's hilarious. All right, anyway. All right, so how many terms do we have to add up in our, well, okay, not just a sub n, but actually 1 over n, right? Because that's the series that we're playing with. All right, so how many terms do I need to go out so that my answer is correct to within a millionth? Well, a bunch, right? But how am I going to figure this out? Right, so what's my error? Error is less than, if I'm going out to the millionth term, well, what is the error? It's 1 over whatever the term I leave off is, right? And I want that to be less than, did I have, yes, that. Okay, so the error is always less than the first term omitted. So let me call the first term I omitted 1 over n, right? And I'm going to solve for n. And I want that to be less than the 0.000001, right? Okay, so let's actually be smart about this and let's write this as 1 over n. is less than 1 over a million. Okay, so what does n have to be? The million and first, right? So n would have to be bigger than a million. Oops. Okay, meaning that how many terms would I have to go out to guarantee that I'm within a millionth? I need to go out to the 1 millionth and first term, and we'll demonstrate, well, actually, no, maybe we won't, because it might take forever for Mathematica to compute. I think you guys get the idea. Okay, all right, so, right. Oh my goodness, how time flies. Okay. Next definition, and this is actually super important. Oops. Need a bit more space there. Okay, so if I have an alternating series, I could just pretend that the alternating part, the -1 to the whatever, isn't there. That gives me a new series, the sort of non-alternating version. Okay, now I have two series on the table. What's possible? One of them could converge and the other diverge. They could both converge. They could both diverge, right? Makes sense. Just, right, if I got two series, well, one might converge, one might diverge. I don't know. Well, they're not. Oh, okay, sorry. If I throw an absolute value around the inside term, then I get my second series. So my two series here are the original is series 1, and the dude without the -1 to the n is series 2. Does that make sense? So I got two series, the alternating one and the non-alternating version. Okay, you guys accept that they both could converge, they both could diverge, maybe one converges and the other diverges, we don't know, right? But all those possibilities are exactly that, possibilities. We have terms for those possibilities. Okay, so if the first one and so it's possible that they both converge. And if that's true, we call the original guy, we say he converges absolutely. Okay, that's why I put the absolute value in there to sort of show you why we use the word absolutely here. Okay. While we're on the subject, what's a mathematician's favorite brand of vodka? Absolute. Because of his absolute value. No, I don't like vodka. It's like drinking rubbing alcohol. Yeah.
You prefer bread water?
Huh? Bread water?
Bread water.
That's beer.
Yeah. Real nice and
Or
watery.
super concentrated bread water, aka bourbon. Um, yeah, anyway, okay. So if they both happen to converge, then we say that the original guy converges absolutely. Okay? If the original guy converges, but the absolute value version diverges, oops, sorry. If the alternating version converges, but the non-alternating version diverges, then we say that the original, the alternating version, converges conditionally. Okay?
Meaning we don't know that.
No, that's not quite what we mean by conditionally, but we'll see in a moment. I think maybe something that'll make slightly more clear why we use that term. Yeah.
Alternate diverges, but the original converges, then we can say that it converges conditionally.
No, that doesn't happen. Right. So, so the question is, what happens if the alternating version diverges, but the original converges? That never happens. Yeah. And it's of course also possible that they both diverge, in which case we've got a divergent series. Okay. So based on this definition, what does the alternating harmonic series do? Conditional or absolute convergence? It's conditional. Why? Well, what does the alternating harmonic series do? Does that converge? Yes, we demonstrated that. But what's the absolute value version of that? The regular harmonic series. And the harmonic series, the regular one, diverges, right? So what does that mean about the alternating harmonic series? It converges conditionally, okay? So it converges, yes, but think about it that we've sort of taken the concept of convergence and sort of split it into two categories. They're still convergent, but this sort of will better enumerate how they converge. Or, yeah, okay. This is really annoying because I'm out of time. All right, so I'm going to post the sheet for today up on Canvas, partly because Dr. Insaldi has to do virtual today because her kid is sick. One of the biggest results about convergence, conditional versus absolute convergence, let me just say it briefly to motivate. If I take an infinite series and I start rearranging the terms, right? So like, let's take the geometric series, 1 plus a half plus a quarter plus an eighth plus a 16th and so on. So let's say I take all those terms and I start rearranging them and I decide to add in a different order. Do I change the result?
The result, the number of what you're converting to,
What it converges to. I'm not omitting terms, I'm just rearranging them.
So are you saying, like, you take it from that, and then, like, are you stopping at a finite value?
No, I'm taking all the infinite series. Okay. Why is it that your gut says that? Because it's addition, and addition, does it matter the order in which you do addition? Okay, so if you add up 10,000 terms and you rearrange, jumble them all up and you add them up again, are you going to get the same answer? If you add up a billion terms and then you jumble them up and add them up all a different way, are you going to get the same answer? If you take an infinite number of terms and you add them up, you get an answer, and then you jumble them up and you get a different answer, are those two answers the same? Well, okay, well, I said different answer, but let's say you took all of them, you added them up, you got a number. You rearranged them, you added them up, you got a number. You have two numbers. Are those two numbers guaranteed to be the same if you added up infinitely many terms?
Yes.
No. 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 It turns out that if you go rearranging a series, you might change the answer. Why? Because we're adding up infinitely many things, right? So you guys saying that A plus B equals B plus A, that's true, but that's only true for a finite number of values. Did we ever say it was true for an infinite number? You're quitting math? All right. And well, which is good because after your that's a B plus sigma comment, you can GTFO. All right. I hope you guys all have a great weekend. And I just ruined addition. I ruined math. No, this is what makes math so much fun. All right. Y'all have a good weekend. Pay attention to Canvas for some updates and stuff. All right. See ya.